hormones communicate within an organism. Semiochemicals, on the other hand, communicate between organisms. And I'm using the word communicate kind of loosely here, as you'll see, because some of these semiochemicals are actually used as weapons. There are two main categories of semiochemicals. On the one hand, we have pheromones, which communicate among members of the same species. In other words, they are intraspecific. And then we have allelochemics, which communicate between species. They are interspecific. Now, some people, not all, further subdivide pheromones into releasers, which are quick-acting, and primers, which are slower acting. Kind of analogous, maybe not exactly, but kind of analogous the way that hormones have their effects, either as activational, that would be analogous to releasers, or organizational, which would be analogous to primers. Now, looking at allelochemics, there are three main types of allelochemics. Allomones, which benefit the sender. That's the most straightforward, and there's many more examples of that in the animal world than there are of these other two categories, probably the most bizarre being cheromones, which actually benefit the receiver, not the sender. And when I show you two examples of that, you'll see why that is kind of bizarre. And then this one's not too bizarre, just not a whole lot of examples of it, and these are cinnamones, which benefit both the sender and the receiver, and we'll only look at one example of that. Now, I'm going to talk about pheromones in a different segment, and when I do, I'm not going to make this differentiation between releasers and primers, so we'll just consider that as one main category. But again, we'll look at that elsewhere. So for now, we're going to focus on allelochemics, starting with allomones. The most obvious, I think, example of an allomone, a chemical that communicates sort of, kind of, between species, again, using the word communicate very, very loosely here, is a skunk. The allomones that are sent out by skunks. Check this out. This dog is about to become very unhappy.
Susie, no, no. Ah, Susie, no. Don't you bite him. Ah. What's the matter, Susie? Something bothering you, Susie? Say. Are you okay? Look at you.
Nice owner. And yes, something's bothering Susie, and she doesn't feel too good about it. The whip scorpion, we're going to look at some insects now, which use allomones a lot. The whip scorpion is really interesting because it can send out its allomone very directionally, as we'll see in this laboratory simulation, as the experimenter probes the appendages with a tweezers. So notice it's now probing, the experimenter's probing the left front appendage, and that white spray is actually the allomone, which, by the way, is very acidic, and so it kind of burns like an acid, whatever would be bothering it over there. And now touching the right front appendage, and you see that the spray is going over to the right. The right rear appendage, and the spray is going to the right rear, and the left rear appendage, and that's where the spray is now being directed. The bombardier beetle, which we've seen in other segments for different reasons, is another sender of allomones, and very effectively. Now, its allomones reach the boiling point, or maybe just shy of the boiling point, when released into the air. They actually mix with chemicals inside right before being released, which then causes them to reach the boiling point as they're being emitted. So no, they're not boiling the poor bombardier beetle from within. And the bombardier beetle does have some protection, as we'll see, from getting burned itself. It has to do with the way it pulses the spray. But here you can see it's very directional. It's pulsing it underneath itself and toward the front. And here we have an experimenter that's touching with the tweezers the right foreleg, and sure enough, it's directing the spray over there. And now the mid leg, and it's directing the spray midway toward the right. The right hind leg, now it's directing it and back toward the right. You can see the rear view. That's exactly what's happening as the experimenter probes the right hind leg. And then it raises its hind leg, and so the experimenter raises the tweezers, and you can see now it's raised the direction of that spray. Very, very accurate.
The bombardier beetle. It can create a chemical reaction within its body so violent that boiling caustic liquid explodes out of its abdomen. By pulsing the jet 500 times a second, it keeps its rear end just cool enough to prevent it being cooked.
And of course, the shot of it spraying was in slow motion. So here we have a bombardier beetle, and there's where the spray comes out of that abdominal tip. And here comes an ant that's going to be very sorry in a second, like right now. And here comes another ant, and it's not even going to get that far. It's going to be shot at in front like that. You can see how directional that spray is. So the way they do it is, if we look at the abdominal tip, you can see the slit where the spray comes out. And then right below it are these reflectors. The reflectors can actually move to help with the directionality. Of course, the slit, the abdominal tip itself moves as well. So the combination of the movement of the tip and then the fine-tuning of the reflectors is what enables the bombardier beetle to direct its spray so accurately. And there's a photograph showing the abdominal tip with the slit and the two reflectors.
All kinds of insects have developed chemical weapons. A pair of devil rider stick insects. They fire bitter-tasting oils, terpenes. European wood ants under attack from a hungry crow. They fire the sort of acid that gives nettles their sting, so this is like one of us falling into a nettle patch.
There's some really nasty things out there. You got to watch where you walk. Okay, pheromones. So the starfish likes to eat scallops, but it emits a pheromone alerting the scallops of its presence, and then they move away. So what's that all about? I told you pheromones, which benefit the receiver, are really, really strange, especially from an evolutionary standpoint. Obviously, the starfish is able to gain nutrition from other sources, otherwise they would go extinct. They would have gone extinct a long time ago. This is another interesting case. The pike is a large fish. These are two freshwater fish, the pike and the crucian carp. The pike is a rather large fish relative to the crucian carp. And these are found in freshwater, and it likes to eat the crucian carp. Well, the thing is, the pike also emits a pheromone that causes a change in the shape of the crucian carp over a period of weeks. So when the crucian carp detects that there's pike in the same lake or pond as it is, within 12 weeks it grows this huge hump on the top of its back, which now makes it unable to fit in the pike's mouth. So the pike is obviously going to have to find other fish to eat. Again, a very, very strange chemical, pheromones. Same with Daphnia, water fleas. So when they detect a predator's pheromones, what happens is they grow these spikes, a helmet full of spikes at the end of their appendage that they can then use to jab at the predator. Otherwise, those spines aren't there. Okay, the final category, cinemones, which benefit both the receiver and the sender. And I only have one example of that.
Like all living things, plants reproduce to ensure future generations. But since plants can't move from place to place, they need a way to transfer pollen from one plant to another. Wind is a major pollinator, but it acts unselectively. Insects, on the other hand, pollinate flowers with precision. The bright colors and strong fragrances of flowers attract insects. Once lured to the flowers, insects discover pollen and nectar. Bees, butterflies, and other insects gather pollen and nectar to feed themselves and their young. As insects move from plant to plant, they transfer pollen from one flower to the next. Fertilization occurs and seeds are formed. Over time, flowers have developed colors, smells, and shapes that successfully entice insects. At the same time, insects have developed features and behaviors that make them more effective pollinators.
Yeah, so cinemones are produced mostly by plants, and in this case, there's an interaction of the plant with an animal, the insect, and both benefit. So the plants benefit by being able to spread pollen carried by the insect, and the insects benefit because they gather nectar from the plants, and they sometimes use the plants also as a mating site. That'll vary from species to species, but nevertheless, that happens sometimes as well. So both are benefiting. And again, it's the fragrance of the plant that is the actual cinnamon, even though they're using vision in combination with that, the color of the plant as well. So those are allelochemics, allomones, charomones, and cinemones.